Welcome to the Rich Report, a podcast with news and information on the world of cloud computing. Today, my guest is from ScaleOut Software. We have the CEO of the company, Bill Bain. So, Bill, welcome to the show today.
Well, thank you very much. Nice to talk to you, Rich.
You bet. So where are you calling in from today, Bill?
I'm calling from foggy Bellevue, Washington today.
Okay, so we're both up in the Northwest. I'm up here in Portland, and it's very sunny. So we've got your sunshine here on this end of the call. So, Bill, I'm curious to learn more about ScaleOut. Why don't we start with your slides, and we'll follow that with the Q&A.
That sounds great. Okay, well, I'll start out with slide number 2, which tells you a little bit about ScaleOut Software. Our company was founded in September of 2003 up here in Bellevue, Washington, and we have offices in both Bellevue, Washington, and down where you are in Oregon, right near Portland, a town called Beaverton. What we do is develop software. Our software is middleware software called in-memory data grid technology. So we build in-memory data grids to help applications scale performance. I've actually worked in parallel computing for many years, going back to Bell Laboratories when it existed, and then Intel supercomputer systems, and more recently Microsoft. And I'm joined by the COO, Dave Brinker, who's not on the call today, but helped produce this presentation. Our products are shipped for both Windows systems and Linux systems, and we have both .NET APIs and Java APIs in our products. Our products are typically used by developers who integrate this middleware software into their applications. So let me give you an example of that going to the next slide, slide number 3. So an in-memory data grid is typically used with online applications that are processing data that's changing very rapidly. And these applications could be hosted on-premise, on a server farm, or in a cloud. Now this slide is showing you an application hosted in the cloud, a cloud-hosted service. An example of that might be a web service or website, or it could also be a social media app or even a number of other applications. I've seen applications that are managing power systems hosted in Amazon EC2 and many more. So these applications are typically accessing data that's hosted in cloud-based storage, either a relational database or a blob store, but they need to be able to access and manage fast-changing data. And they need to also be able to scale as they handle larger and larger workloads. So in-memory data grids provide the answer to the question of how do you store data in a way that allows the system to scale and to handle the data that's changing very rapidly. So in-memory data grids are typically hosted across a set of servers, and these servers are accessed by the servers that make up the application. You can see in the slide here the application servers are shaded with the dark blue, and then the light blue shows the grid. And so the grid servers are hosting this data and serving it up to the application and allowing that application to get access to this fast-changing data very rapidly. Examples might be shopping carts in an e-commerce app or financial market data that's streaming through a financial trading system, and we'll talk more about financial trading systems in just a minute. So going on to the next slide, slide number 4, this shows you the key benefits of in-memory data grids. I mean, really the key benefit is to make data access fast and to maintain fast access as the workload grows. And also to manage this fast access time by scaling the throughput of the grid so it can handle larger and larger amounts of data, make that data available to all of the servers that make up the application, and then to keep the access time very fast while all of this is happening. So if you look at the chart on the bottom right of slide number 4, it shows you here the throughput of a relational database that doesn't scale with the red line, and the workload is increasing as you move from left to right. You can see that what happens is the access times start to climb as the database server runs out of capacity, and at some point the throughput of the database server maxes out and the access latency just goes up straight up. Now, in-memory data grids and other scalable storage systems like blob stores in cloud systems, the so-called NoSQL stores, file-based stores, but more importantly for today, in-memory data grids, which are also a form of a NoSQL store, they will scale their throughput by adding more servers to handle the workload, to handle more data that they're serving up, and they'll keep their access time fast. If you look at the bottom left, it shows you how an in-memory data grid is faster than a database in retrieving data, and that's because it can cache data at various levels in the memory hierarchy and make it available to the application very quickly. Now, one thing that in-memory data grids provide that's important is high availability. They provide the ability to keep serving data and to not lose data if one of those grid servers goes down. And that's very important for these online applications, which are typically mission critical, and money is lost or other problems will ensue if data is lost for an online system. So in-memory data grids integrate high availability into their management of data. And as I mentioned, they allow the data to be accessed by any server in the application. And this shareability helps simplify the structure of applications. Now, another characteristic of an in-memory data grid is that it can span multiple sites. It can be used both, say, on a cloud deployment and also in an on-premise deployment. And by spanning multiple sites, it can allow data to migrate between sites transparently. So you have the effect of a virtual data grid that spans multiple locations. And this simplifies having applications burst into the cloud to handle large workloads or to just have applications that span multiple sites. Now, the topic that's really of interest today is how do you analyze data that you're holding in the grid? And it turns out that online applications really need this ability to analyze the data that they're storing and that's flowing through the grid very rapidly. And in-memory data grids provide an excellent platform for hosting this analysis. So let's go on to slide number 5. And that shows some examples of online systems that can benefit from real-time analysis of the data that's flowing through the grid. So let's look at first an equity trading system of a stock trading platform. Now, in this case, you might have stock market prices flowing through the grid throughout the course of the trading day, and a trading application that wants to look at both the market data and also, say, news items, and then to look at its portfolios of stock positions and make intelligent trades based on looking at all of the data in the grid as it's flowing through. So here's an example of an application that really could benefit from this parallel analysis of all of the data that's in the grid. And we'll look in detail at how that might be implemented in some upcoming slides. Another example, of course, would be an e-commerce site, like a website that's looking at real-time shopping activity to identify trends and patterns during the shopping day and to optimize the overall shopping experience for its customers. So, for example, if if a lot of customers were looking at one type of garment, say red sweaters, then the site might want to create some special offers on red sweaters at that time of day, or to be able to look at individuals throughout the shopping site and identify what they're looking at, what's of interest to them, and to make special offers to individual customers. Now, reservation systems, for example, an airline reservation system could benefit from real-time analysis of the data in that system to identify all of the customers that need rerouting and to manage that rerouting very efficiently and to identify other issues. Credit card systems, and one of the problems with credit card fraud detection systems is they typically do not respond in real time while a customer is making a purchase. However, using an in-memory data grid to store credit card transactions and in the ability to examine all of these transactions in real time allows sites to be able to identify potential fraud and respond to it within a few seconds and thereby to avoid the cost of fraud. Now, power systems is another example, and military systems, manufacturing systems, gaming systems. There are many other applications that can benefit from the ability to analyze real-time data for an operational system and respond very, very quickly. Now, the big problem we see in slide number 6 is that traditional big data platforms that have become very popular over the last couple of years, a typical example is the open source Hadoop platform, and of course there are other proprietary platforms that do what is called map-reduce analysis, which is another way, a very specific form of what's called parallel data analysis, looking at an aggregate set of data and then finding the patterns and trends in that data and reporting those results. These types of systems typically analyze what we call lakes of data, as shown in the picture. These are large static data sets which are typically offline. And not only is the data typically offline, but often the data has to be moved from another location, another disk-based storage system, into a file system specifically used by the analysis platform. So, for example, analysts often will move data from a data warehouse into the Hadoop distributed file system for analysis by Hadoop. So we have copies of data across the network and file I/O into Hadoop to do the analysis. And all of this means that the analysis can handle very large data sets, but it can't necessarily respond in real time. And moreover, these systems acknowledge the fact that they're not really running in real time, and they offer batch scheduling. Hadoop is a batch scheduled system, so that the results may come out after several minutes or hours, but the intent is not really to handle this analysis in real time, but to handle very large data sets and do so over the course of minutes and hours. Now, if you go to slide 7, you can see that in contrast to this, an in-memory data grid naturally is integrated into an online system, an operational system, and it is handling data that's flowing through, we call it rivers of data instead of lakes of data. So an in-memory data grid is handling a river of incoming data flowing into the grid, updates that are flowing into the grid, and being read out by the applications that are using the grid. So this is an ideal platform for doing analysis, parallel analysis of the data in the grid by performing a MapReduce style algorithm on this data, and by doing so on data that's already hosted in memory and doesn't have to move either across the network or from a disk into memory for analysis. So this very efficient storage of data and the ability for the grid to handle many parallel analysis requests at once across its grid servers, so it's naturally parallel platform, gives it the ability to do MapReduce analysis very, very quickly and in real time. So let's look at an example of this, going to the next slide, slide number 8. And this shows you that stock trading platform and how it can use a grid to host data and to analyze that data and how that would benefit the application. So this stock trading platform is looking at market data that's flowing in, say stock prices that are changing through the course of the trading day. These are being stored in the grid as a pool of objects, one object, say, for every stock symbol. So like AT&T or IBM, each would be an object, and the history of stock prices over the course of minutes, hours, perhaps days and months can be held in the grid as a logical collection of objects representing these various stock symbols. Now, the trading application can reference and access this stock history to make decisions about which stocks to trade. And of course, it can also store other types of data like portfolio data for the customers of the trading application. Now, the ability for the grid to host a risk analysis platform in addition to the trading platform is what gives this in-memory data grid the ability to respond in real time. Because this risk analysis algorithm can look at the aggregate set of data that's being stored and flowing through the grid, analyze it, find patterns and trends, and to optimize the behavior of the trading application. Let's see how you would actually structure such an application. So going on to the next slide, slide number 9. The first step would be to have the risk analysis algorithm query the sets of data that it would be interested in. So for example, if it was interested in the tech sector and maybe stocks in the Northwest region, just as an example, it can query all of the objects in the grid which are holding stock prices that correspond to those particular companies. Now, of course, the range of queries could be very broad. It could look at market cap. It could look at many other aspects of these stocks and query on the properties of these particular companies. Now, because the data is being stored as collections of objects, which are being accessed typically by Java or perhaps .NET code, it's very natural to write a query specification to identify the objects of interest. Now, these objects of interest are not pulled out and read out to one application running somewhere else. They're just identified in the grid, and these objects are spread across all of the grid servers. So we have parallelism in the lookup here, and now we'll see in the next step we'll have parallelism in the analysis. So going on to slide 10, the next step after selecting the objects is to analyze them. And the analyst will typically write a method, which is sometimes called a map method or an analyze method, which will look at an individual stock or object, in this case a stock history, and do some evaluation as to what the trend is with the price changes over time. Perhaps make a decision about whether this is interesting as a candidate for a trade, perhaps provide a return on investment for that trade for a given portfolio. So the analysis method then looks at the data in each of these objects that have been selected by the query, and then these output results are merged by another method that the analyst writes called a merge method, and sometimes called a reduce method. Now, this is a special form of the well-known algorithm called MapReduce that's being implemented in the grid here, that's merging, doing binary pairwise merging of the data, but other forms of merge or reduction could also be supported by the grid. In this case, the merge method is looking at two sets of results and combining them, perhaps selecting the stock that's of more interest, and then over a parallel reduction, all of the stocks are being analyzed and then and their results merged until we finally have on the far right here a merged set of results, which is reported to the trading application. And this set of results can be used by the application to optimize its trading pattern so that it can obtain the best return on investment. So you see here a parallel analysis starting with a query, followed by an analysis in parallel of all of the data that's been queried, and then finally followed by a merge of all the results to provide a set of results that can be used to identify a pattern and trend that's of interest. Now what we did was, and if you look at slide number 11, the next slide, we hosted this platform on Amazon EC2 just to show how powerful the in-memory data grid technology can be for doing this type of real-time analysis of operational data. So in this case, we ran a 1 terabyte data set of stock history data that we were hosting on 75 servers. They were 64 gigabyte servers in Amazon EC2. And then what we did was fed that grid a continuous stream of updates to all of the stock ticker symbols, all of the objects held in the grid, at an aggregate rate of about 1.1 gigabytes per second. It's a pretty hefty update rate, and that represents the change of stock prices over time as the market evolves during the workday. Now, the next step was to perform MapReduce analysis of all of the data in the grid all at once, and we were able to demonstrate that we could analyze the full terabyte, all of the data in the grid, in 4.1 seconds while these updates were streaming through. That's the green line in the graph on the far right, and it shows you that we were actually analyzing data at the rate of about 250 gigabytes per second. So this shows you that an in-memory data grid can respond to the analysis of a very large data set in just a few seconds to give very meaningful and important results, and can look at all of the data in the grid, provide some reporting on the patterns and trends it's seeing, and be able to continuously do so over the course of the trading day. And while this grid is also hosting updates arriving at a very high rate, in this case 1 gigabyte per second. Now the red line and the blue line show the behavior of the analysis as we reduced the update rate. So the red line is a lower update rate, and then the blue line represents no updates at all. So you can see that the analysis throughput goes up as the update rate goes down. But even at a really high update rate, you still can do very, very fast analysis of the data in the grid. So this really is an important new opportunity for applications that are online to be able to analyze data that's flowing through their systems in real time. So looking at slide 12, let me just wrap up by saying what we're doing here is helping applications which are processing online data that's changing very rapidly both scale their performance and provide real-time analytics on the data that they're managing in the grid. And this is really an opportunity that has not been addressed by the conventional big data analytics platforms because of their focus on static or offline data sets. So we're very excited about this new technology, and we're very happy to be able to tell you about it today. So thank you. And what questions might you have?
Well, Bill, kind of, from the 10,000 foot level, do I have to rewrite my applications to run in this environment?
Well, typically applications that use an in-memory data grid use the APIs of the grid, which are very simple. They're like file system APIs, and they're integrated with Java or C# to allow the application to store data in the form of objects, Java objects, C# objects, directly in the grid. So they really look very close to the in-memory collection mechanism that's already built into these languages. In Java, it's called the map. And so the data in the grid is very naturally accessed and queried by a Java or a C# application. So yes, the APIs have to be used to store the data and retrieve it, but that work is a very small jump from what's done for data that's already stored in memory in the form of object collections. Now for the analysis phase, yes, these analysis codes, as I showed in slide 10, I'm just going to bring up slide 10 here, the analysis and merge methods are written by the programmer to do this analysis of the data in the grid. However, these methods are very natural extensions of what Java and C# programmers already do today, because they're class methods that are defined on the types of objects that are stored in the grid, and so they represent a very natural extension of the application itself. So the amount of work that has to be done is very slight, and and very natural for the application developer. And it represents actually a great simplification over systems like Hadoop, which have more complex mechanisms like record readers and reducers and record writers to convert data from a file system format into an object format or a map or key value pair format for access by the analysis methods. So we find that one can write these analyses very quickly and get results very, very quickly.
So, Bill, along those lines, from a hardware standpoint, does one need to use specialized hardware like really fat nodes with very large memory to take advantage of this platform?
No, actually, this type of middleware software is designed to run on conventional commodity servers or in virtual servers in any of the cloud environments like Amazon or Windows Azure. So you will find that this type of software will run anywhere that applications will run on a server farm.
Sure.
It does not require special hardware.
Great. So you mentioned, running on AWS. Is the ScaleOut some kind of module that can be loaded from that side, or how does the installation and licensing work?
Okay, that's great question. Yeah, we are in the Amazon Marketplace, and you can go to the Amazon Marketplace and select a variety of applications or middleware that you might want to use in your application. So we're listed there, and what you do is you license the product from Amazon and pay on an hourly basis, and you can select the type of server you want to run on, an extra large, or a small server in Amazon. And then at that point, you bring up our console and just deploy, using your Amazon credentials, you just deploy the number of servers you need. And then we provide a means by which we can automatically connect an application that's running in Amazon or on-premise directly to the grid servers with a very simple configuration step that's done by the customer through our console. So we've taken many steps to simplify the deployment and management of the grid in Amazon or Windows Azure by using our management console that runs on your workstation.
Well, great, Bill. Well, kind of a wrap-up question here. How easy is it to kick the tires on this and see if it'll work for my application?
Well, it's as simple as going, if you want to run in the cloud, it's as simple as going to the Amazon Marketplace and signing up. Or if you want to test this product on-premise, then you simply go to our website and download the product and try it out. And so it's a very simple process to write your first Hello World program for an in-memory data grid, and we have many samples of how to use this technology and to build analysis applications.
Well, terrific. Well, Bill Bain, I want to thank you once again for coming on the show today.
And Rich, thank you so much for the opportunity. We're very excited to present this.
Okay, great. All right, folks, that's it for the Rich Report. Stay tuned for more news and information on cloud computing.